Hello everybody. In this video I'm going to talk about LeChatelier's principle. And LeChatelier's principle is all about a system that is already at equilibrium and some kind of change is imposed on the system. There's some kind of stress, something changes, and the equilibrium is going to shift in a way that will reduce whatever change was made. And that's the key thing here. It's the system. I know these reactions, they don't want anything because they're not living things, but if it helps you think about it that way, you can think about it as the reaction wants to minimize whatever change was made. Right now, a little part of this, a minor part, is that pure solids and liquids are not affected by changes in equilibrium. And that is because they are 100% concentrated. LeChatelier's principle all has to do with changing a big part of it has to do with changing concentrations, right? And since they're already 100% concentrated, if I have a pure solid and I add more solid to it, or a pure liquid and I add more pure liquid to it, it's still 100% concentrated. It's something that doesn't come up that much, but it will every once in a while. All right, now, if we talk about changes in concentration, if you add any kind of substance to a system, it is going to try to consume whatever that substance is. It's going to try and use it up. Right? And if you take a substance away, it's going to try to make more of it. Right? Remember, to have the systems in equilibrium have a tendency to try and minimize whatever change was made. So if you add stuff, it wants to use it up. If you take stuff away, it wants to make more of it. Now there's a reaction here, and I'll end up doing a demo with this in class. N2O4 going to 2NO2. And they end up both being gases. And there's different things you could do. And a lot of times what scientists will try and do is maximize whatever product they're trying to make. So what we're going to do is look at some things we could do in terms of LeChatelier's principle to try to do that, right? Whether it's adding or removing reactant or adding or removing product or changing the temperature or changing the pressure or volume. That's all the kind of stuff we're going to get into. And now if we talk about changing pressure, remember, like when we're doing the gas unit, when you hear the word pressure, first thing you should think of is collisions. So if the pressure is increased, basically you're saying you're making more collisions, the reaction is going to shift in the direction that will minimize those extra collisions, that extra pressure. And that is the side that has the least number of molecules. And it's easy to figure out the number of molecules. You just look at the coefficient. So sometimes people say molecules, sometimes they say moles. It really gets to the same point with this. I have 2 moles of NO2 gas as the reactants, and I have 1 mole of N2O4 as the product. So if I increase the pressure for this system, I am causing more collisions to happen. Now the system is going to try and minimize whatever those collisions were. So it's going to shift to the right because 1 mole of a gas will collide less than 2 moles of a gas, which means 1 mole of a gas has a lower pressure. So remember, if I increase the pressure, system will have a tendency to decrease it. Now for this one, there's 2 moles of hydrogen peroxide that are going to form 2 moles of water vapor and 1 mole of oxygen gas. So if I increase this pressure, well, now I have to look, there's 2 moles of gas on the left and a total of 3 on the right. So if I increase the pressure, it's going to try and minimize whatever change I made. So if I increase the pressure, I cause more collisions. It's going to try to go to the side that has less collisions to minimize it. So it's going to shift to the left because 2 moles of gas will collide less than 3 moles of gas. Now this one has 2 moles of gas on each side, so it's not going to shift in any way. I could change, increase, decrease the pressure. It doesn't matter. 2 moles of gas on the left, 2 moles of gas on the right, so there's no change there. Remember, pressure only affects gases. It's not going to affect solids or liquids. Now, temperature, it depends on whether it's exothermic or endothermic. Exothermic reactions are reactions that release heat to the surroundings. So heat is a product. This is where delta H would be negative. And when you're talking about this stuff, think about heat as if it was any other chemical in that reaction. Now, if I lower the temperature, so I'm taking away a product, what's going to happen is the reaction is going to try to remake whatever product I just took away. So the way it's going to do that is to shift to the same side. It's going to make more of the 2HI and the heat. So if I want to maximize the amount of HI, hydroiodic, that I have, what I could do is put this stuff in an ice bath. It's going to take away some heat, and the reaction in the process of making heat, it also makes the other product. It can't just make one product. The way it does that is by sacrificing, basically by consuming more of this H2 and I2 to make these products. Because remember, that's how the products are made. The H2 and I2 react with each other to form product. Now, let's say if I increase the temperature, let's say I put this on a hot plate or something like that. What's going to happen then if I increase the heat, the equilibrium is going to shift away from it. It's going to try and consume some of that heat. And the way it consumes some of that heat is by sacrificing some of this HI. It uses this HI to react with that excess heat, because there are the things that react together. So the 2HI reacts with some of that excess heat, and it's going to remake some of those reactants. So I get a higher yield of hydrogen and iodine, which usually you don't want. Usually you want to maximize the product. So remember that if you take away a substance, equilibrium is going to shift to the same side because it wants to make more of it. And if you increase it, like here I increase the heat, it's going to shift to the opposite side because it wants to use up that excess heat. Now, endothermic reactions. These are where heat is a reactant. Heat is needed for this reaction to occur. So this is when delta H is positive. If I take some temperature away, if I put this in an ice bath, so I'm taking away heat, the equilibrium is going to shift to the same side because it wants to remake that heat. And in the process of remaking it, it's going to make more ammonium chloride. Now, the way it makes more of the reactants is by using up the ammonia and the hydrochloric acid. Those get consumed in the process of remaking reactants. So if I want to maximize product, this is not what I want to do for this one. Now, if I increase the temperature, if I put this on a hot bath, if I put this on a hot plate or a hot water bath or whatever, if I increase the heat, now equilibrium is going to shift away from it. It's going to use up some ammonium chloride to react with that excess heat, and I'm going to make more ammonia and hydrochloric acid. So remember, if I add something, equilibrium shifts to the opposite direction. Homogeneous and heterogeneous equilibria, just a little bit of vocab here. Homogeneous just means everything's in the same state, whether it's all gases or all aqueous phase or whatever. And heterogeneous just means you have different states. You might have gases, you might have liquid, you might have a solid in there, whatever the case is. All right, now, what's good about LeChatelier's principle, what I think works well, is what I tell people, because I see this as a pretty common mistake, is people try and memorize, or at least some people trying to memorize all of the different variables, all of the different circumstances you can have with this. And there would be a lot, right? If you try to memorize it and you just make one little mistake, it's going to throw everything off. It's really much better if you just understand the concept and reason it out. So if I add reactant, that is disturbance. The system was at equilibrium, and I know it seems silly to think about it like this, but you can think about it as it was in its happy place, right? And then I went and messed something up. I added some reactant to it, so I increased that concentration. Well, the system has a tendency to consume that extra reactant, or you can think about it as it was happy with the amount of stuff it had in there. I added more of a reactant, and it wants to get rid of it. So that extra reactant, or some of it, is going to get consumed, which means it's going to shift to the product side. The new equilibrium is shifting to the product side because it's shifting away from the reactant. Now, if I add product, it's going to try and get rid of some of that product, so it's going to consume it. So equilibrium is going to shift to the left. Remember, if you add something, equilibrium always shifts to the opposite side. Reactants are on the left, so equilibrium shifted to the right. And whatever is on the right, you're going to get more of, so more product. Now, if I add product, equilibrium is going to shift to the opposite side. So it's going to shift to the left, which means I would get more reactant made. Now, in terms of volume and pressure, you can kind of think about this whatever way makes more sense to you. A lot of times I tend to think about it as in terms of pressure collisions. It just makes more sense to me, but whichever way works better for you. So if you decrease the volume, you're going to cause more collisions to happen, which means more pressure. Because remember, pressure and volume, that's Boyle's law. They have an inverse relationship. So I cause more collisions. So equilibrium is going to shift in a way that will reduce or relieve some of that pressure. So it's going to shift to the side that has fewer gas molecules, right? So increased pressure means more collisions. It wants to reduce the collision, so it goes to the side that would have less collisions, which is fewer gas molecules, which you figure out by looking at the coefficients. Now, if I increase the volume, the particles are going to collide less with the walls of the container, so pressure is going to go down. Well, it was happy the way it was, and it wants that pressure back, if you want to think about it that way. So pressure is going to increase. It's going to shift to the side with more gas molecules. Now, if the temperature is increased, it's going to try and get rid of that extra heat energy. So it's going to consume it, because remember, think about heat as if it was a chemical at this point. It's going to shift in the endothermic direction. That is the direction where heat is used up. And if it drops in temperature, heat energy is generated, right? You took heat away. It wants to get it back to where it was. So it's going to shift to the side that is exothermic, where more heat is generated. Right, so remember, when you're doing LeChatelier's principle, it's all about the system was at equilibrium. There was some kind of change made. So it's going to try and minimize that change. Now, in reality, it's never able to completely get rid of everything. So let's say I add reactant in this case. It's never able to consume all of it. I'm still going to have a little bit in there extra, right? But it's going to try and minimize with the changes. And the way it does that is by shifting it to the right. So if you add a reactant, let's say there's 2 reactants, it's going to use one of them to get rid of the extra that you added from the other one, right? So you're going to force those things to interact more, to react more, and you're going to make more product. I know we're going to end up going through a bunch of examples of this stuff in class, which I have other videos for that.